So one idea is to do a star search for this, because this is a discrete space. There are only so many configurations. But another idea is to start with a configuration, because in the end you are looking for a configuration that has some good properties. The property being the number of conflicts is minimized. You're hoping it will be zero, but you really at least want to minimize it. So I take this and I say, this is a configuration. Is this a solution? If the number of conflicts in this is zero, then it's a solution. If not, then I need to make a little change to the configuration. What I would do is, for example, I'll change one of the queens. In its column, I'll move it up or down. You see what I'm saying? So the question then is, if I get to move this queen in different ways, there are different possible places where this fourth queen can be put in this column. For each of them, I can compute what is the number of conflicts. So I know for each option how much is the reduction in the number of conflicts. And then I pick the choice that reduces the conflicts the most. Do you see what I'm just saying? This is just discrete version of gradient. This is just discrete version of derivative. And solving NP's problems optimally, solving NP's problems efficiently for NPs of size million, and you might be wondering who are these bozos who want to solve million by million chessboard, where they want to put million queens such that no pair will compete with each other. There are such people. And turns out that trying to do those problems with A-star search is basically very wasteful. Instead, you just go with this gradient search. Now, if you do it in discrete space, you typically call this hill climbing. This is actually described in the informed search, right after the informed search chapter in the textbook, called local search methods. All gradient search is local search for continuous spaces. And in general, local search tends to have all sorts of problems. If you are trying to do hill climbing on a hill, trying to decide, suppose you are, for example, somewhere here, and you're trying to climb to the hill, you are likely to come either here or here and stop. Because after you come to either of these places, to make any local moves, your elevation reduces. So then you say, I have come to the place, I shall call this the peak of the mountain. Then you will be Columbus. Columbus was looking for India, and he according to his map, basically there was just water between Europe and India. And so he kept going until he hit land, and that happened in Cuba, and he said, that is India. Okay, so he did. So in this particular case, the local search basically. So and again, another in terms of mountains, hill climbing is great for what mountain? Those of you who climb mountains. Zermatt. The Zermatt is the Zermatt Matterhorn. The Matterhorn is the mountain that you see in the Disney World, Disneyland. That thing has this really great peak. So if I put you somewhere to the base of the mountain, and if you just keep making local moves that keep increasing your elevation, you will eventually reach the top of Zermatt, top of Matterhorn. It's a completely useless method for going to the top of Everest, which is like the tallest peak in the world, or Mount Whitney, which is the tallest continental United States peak. Geography lessons like that. Okay, because it so happens that all those peaks are surrounded by peaks that are almost as high as them. And so if you do local search, you will reach one of the minor peaks. And if you're Columbus, then you turn the other way, because there is Everest outside, and say, this is Everest, I'm standing on it. Okay, that's what local search does. So when you are optimizing, you are finding a reasonable optimum. You are no longer guaranteed that you found global optimum. And if you remember calculus, the way you found the optimum for a function in a particular range is you found all its stationary points, all the minimas and maximas, enumerated them, and found which was the biggest, and that was the real maximum. You never do that. You never do that for real gradient descent search because it just becomes too costly. So that also explains how to make gradient descent a little more optimal, a little more closer to real optimum. So there is this problem of local minima that you keep hearing about with respect to any local search. Any search that doesn't keep track of an open list, it can get stuck in local minima or local optimum. And the way you handle that is essentially, one idea is you randomly restart. So you put yourself in a different part and start climbing again. And if you with a good chance, you might find a different peak this time. And this is something again we wind up doing in learning methods for essentially gradient descent. So you wind up starting multiple times, for example. Okay? So anyway, coming back to this, so basically you do gradient descent, and if you want to do gradient descent in this particular problem, I'm going to just complete this, it'll probably take 5 minutes and then we'll end with that. So I have a function v theta, which if you remember was this. I know the features of a state, I know the current weight values, current theta values. So by plugging the features into this function, I will get a new value for that state. Okay? That is what I am predicting the value of this state to be. And imagine I happen to know the actual value of the state. So it's like knowing the real grade of the student from the past semester. So that is the true value, and this is the difference. And you want your predicted value to be as close to the true value as possible. One idea is to essentially take the difference, square it, sum it up. Why square it? Because the pluses and minuses should not cancel out. So in fact, a better idea is to take the absolute values of the differences and add them. Why won't I do that? Because if you remember the way absolute value function looks, it is two lines. There is no, it's not differentiable at the place where the two lines meet. This is another thing that you will realize. If all you have is a hammer, you will make everything look like a nail. Okay? If all you have is a gradient descent as your vehicle of choice, you want to make sure that your error functions are not only continuous but they are differentiable. So, then why half? Why am I minimizing? So this is the error and I want to minimize this. Why am I taking the half of the error? Somebody from one of those endpoints who have had good sleep already by now. Why are we taking half of the error squared? What is the differential of x squared? What's the derivative of x squared? 2x. The 2 and 2 will cancel out and you feel really good. Do you understand what I'm saying? It looks like the silliest reason to do it, but everybody does that. They define error as half of the squared error. And it looks like using thetas, putting half makes you look very sophisticated. But the reality is, it's just somehow you feel good that there is no half factor behind error. So if I actually optimize half of the error, have I optimized the real error? If I optimized pi times the error, have I optimized the real error?
Yes.
Yes. So it really doesn't matter one bit or other. It just somehow makes people feel good that the 2 gets cancelled out. And cancellation is the reason you want to live. Yes.
Does squaring help with optimization at all?
No. Yes, actually that's a very good point. Bring it up next class. It turns out that squaring, which you do because it's continuous error function, winds up having negative, aspects to it. And so in fact, people have figured out how to live with absolute error. And this is basically what's called the L1 regularization. So basically, if I have this, and then by now I'm actually changing the thetas, I change each theta in the direction that is the partial derivative of the error with respect to that particular thing. Okay? And then, of course, how much to change? This is the learning rate alpha. And I change it in the opposite direction because I'm trying to minimize the error. And the only question is, of course, how do I compute dou E by dou theta? That I will use the actual chain rule. So E by dou theta is dou E by dou B and dou B by dou E. And if I go there, then this will be, remember I have this whole thing squared and I'm doing it only with respect to V theta. So I would get the half cancelling out and this piece will be the derivative. Because remember, you have got 2 times this quantity, that 2 and 2 gets cancelled out, so you get just that. That is the part corresponding to this. The second part is dou V theta by dou theta, right? That, how do I figure that out? How do I compute the derivative of V with respect to theta? I remember how I defined V. Dou V by dou theta 1 will be just F1. Because if you are differentiating with respect to theta 1, all these other guys are constants, so they become 0. You see what I'm saying? So, that's basically what I wound up doing, and then this becomes F1. And I know all these values, and I know how to change the theta every time. I'll stop here. In essence, this directly changes the value function estimate by changing the theta, the beta. Okay.
Trust.